Hello, and welcome back. Today, I am very happy to show a pathfinding algorithm that we will be using to put to work the navigation mesh generated in the last few videos. Luckily, most of the work has already been done, and the nav mesh is configured in such a way that we're able to leverage the convexity to create very fast pathing queries. It's been a long time coming, so let's jump in. Before we begin computing the actual path, we'll need to determine where the start and end polygons are. There's much better ways of doing this. However, for the sake of not having to hold this back longer than needed, this is how I get the polygons. We'll go over every polygon in the nav mesh and first determine whether the point is above the plane and within the threshold. If it is, then we check next to make sure that the point is fully contained in the polygon. This is done by computing the side planes of each edge and ensuring that the point is within some tolerance of the positive side of the plane. If each edge passes this check, then the point is fully contained in the polygon, and the polygon is returned as the candidate. In real-world situations, you would still want to detect containment, but you can easily just project each polygon onto the XZ axis and compare the 2D cross product sign of the edges in the query point. You would also want to wrap this all up in some kind of acceleration structure to avoid checking every polygon. Something like an octree or quad tree should suffice. Now that we have our beginning and ending polygons, we're good to begin the pathing algorithm. The algorithm itself begins by calling portal DFS, and we supply the arguments in reverse order. So we're going to start at our end location and route back to our begin location. To demonstrate this design choice, I want to walk through an example of how the overall algorithm works. The first example is rather simple to show the basic concept. As mentioned before, we start here at the end. We create a search direction from the end to the start. For each portal in the polygon, check the intersection point. If needed, project the intersection point onto the portal. In this case, we have only one portal and we select this as the next point. Now, we repeat the same steps as before. Since we have two portals, we choose the one with the smallest distance error. I'll show the actual formula later, but for now just take my word, it's this point. Once more, we repeat, and we can go ahead and skip through since these two portals overlap and we'll have zero distance error. Now when we expand the next search, we detect that the polygon in question contains our start location and we have our path. Now let's move on to a more complex example. I'm going to walk through the pathing and it should become obvious where the errors are. Now here's the first issue. The distance error chosen led to an incorrect path. However, due to the DFS nature of the search, this polygon will detect that it's unable to expand towards the start location and will kick the search space back to this polygon and we'll end up selecting our other point here. And now we can see the second issue. The first half of the route is Euclidean optimal. However, once the path bends in the route second half, we have this very large detour that happens. Again, this is actually a non-issue due to how the paths are generated in practice. Because the AI thread works on a snapshot representation of the simulation, every time the planner creates a new plan, it doesn't check a cache but rather recomputes the entire thing. This is so that the dynamic changes in the simulation can be caught without having to deal with the read-write nature of updating cached desires and actions. So how does it take care of itself? Well, let's assume that the endpoint doesn't move, but also assume that the drone has made it along the path from S to the midpoint. When the path gets recomputed, we see that the detour ends up bending back inward and the actual route that gets taken by the drone in practice is Euclidean optimal. Now that we have the basic idea, let's go ahead and look at the code. As mentioned before, we're going to begin our DFS starting at the end location and searching in the direction of the start location. We're also going to keep a deck of points that will be used to push and pop generated waypoints as needed, as well as a set of polygon indices used for tracking visited polygons. First, we'll check to see if the polygon we're searching in is the one we want. If so, return true and validate the current path that has been generated up to this point. If this fails, we next check to see if we've come across this polygon before. If we have, then we want to return false and tell the algorithm to remove the part that led to this polygon. If both of these checks fail, we insert the polygon into the visited polygon set and begin computing the rankings for each portal in the current polygon. For each portal, we're going to first check if the visited polygon contains the twin polygon. If so, we skip this portal as it will just lead us back to a place we already came from. Next, we'll compute the traversable location. If the portal gate is small enough, we just return the portal vertex and call it there. Else, compute the intersection point of the search direction and the portal, and then clip the point against the portal. After computing the traversable location, we'll compute the distance error. This error represents how much of the total distance this current path segment veers off of the optimal path, which is a straight line. Finally, we compute the next search direction from this location and insert the portal ranking. Once we have all of the portals ranked, we'll begin expanding the search starting at the first portal. Insert the portal's point into the waypoints and then begin in the search direction. This repeats until either a valid path or the entire search space has been exhausted. One thing I would like to explore in the future is taking this distance error a bit further and exploring a technique where we probe the next path and accumulate the error. I believe this might be useful for when handling issues as shown before where a dead end has the best distance error at the local evaluation. However, I'm not sure if the compute overhead is worth it and will require more testing. However, for now, this is really all is to it. Once the portal DFS function returns, we copy over the waypoints and insert the final end location which the algorithm started from. The result now contains the complete path the drone will be instructed to follow inside the simulation thread. That is all for today. Very short and sweet, and that was really by design. Pathing can be an incredibly expensive calculation to perform, and so I chose to trade off the complexity in building the NavMesh in hopes to extract out a set of relatively large convex pieces. Convex pieces have a nice property about them that if you take a straight line, you're guaranteed to never leave the polygon. Thus, I wanted to leverage this property as computing straight lines over and over should be much more computationally cheaper than something like a star. I also know that it may seem like a really weird design choice to not cache things, however, in the next part of this series, I believe it will make a bit more sense. I've kind of alluded to it in this video with the complex pathing overview, but the entire system is designed to be a series of constraints that are evaluated, and if a violation is detected, desires are generated to restore the expected state the system is looking for. Before I forget, I've gone ahead and put up all the relevant code used for the NavMesh generation and the pathing used in the last few videos, so feel free to check it out. Thank you though so very much for your time today. I hope you enjoyed this one, and I cannot wait to see you in the next one.